Okay, so welcome everybody. So as Andre very kindly said, my name is David Atienza. I'm quite new in EPFL. I'm not sure if it's really true the part of the champion, but I really appreciate the comment. What I will try to illustrate is a little bit what I have been trying to build since I joined at the end of 2008 in the Embedded Systems Laboratory, which is basically a mixture between research and involvement of companies to do technology transfer. The main reason for doing that is simply because in our area of research, which is related to computing engineering and electronic systems, we cannot really build in many of the areas, as you will see in a second, without having the support of the companies. Because many of the technologies that are required to be at the forefront of the research require the information coming from the latest technology nodes and latest devices that are coming from companies that actually are on the market. So in that sense, like I said, let me start by introducing a little bit the structure of the lab. So like I said, the lab is quite new, it started in 2008, and now after roughly 5 years already, we were stabilized in 25 members. You will notice that it's a little bit large with respect to other labs at EPFL. The main reason for that is precisely the effort I mentioned on the technology transfer side. So we need to have a reasonable amount of senior researchers and postdocs to be able to support the structure. Why? Because the situation that we are and the relationship that we have with the companies do not tolerate to have delays on developments or things like that for them. So that requires to have a person that is more dedicated or more willing to actually spend the time on the implementation in some aspects that are not pure research, which is what we really truly make the PhD students focus on. So you will see that we do research in combination, but there is not a single PhD student in my lab dedicated to interfacing with the company on the development of the ideas or the projects or products for them. These are always done with the postdocs. Actually, in fact, now you go on the website, you will see that we have 8, but it's a transitory period. Typically, we are between 5 to 6 postdocs in the lab. Okay. At the same time, like what Andre mentioned, we are focused on research. So in that sense, we have a large amount of PhD students because we're working in different areas, and typically the students work in groups of 2. You have a junior one and a senior one, at least. Okay? In some areas that are large, we have 3. But the idea is to have at least 2 working with the postdoc as well and being supervised. I follow all the groups that we have in the team. Okay? So that's the idea. Then we have a number of a number of master thesis students that come and live in the lab. So they have a round time of typically between 9 months and a year, depending on the project. So in some cases, EPFL only requires 9 months, but the students are willing to go further if we propose them topics related to companies and they stay a bit longer, for example, for the summer, after the actual due time with EPFL is done, to really implement the full system on the company. That's what they like. So based on that, what we have been, to be able to support this structure, we have been trying to build, of course, support PhD students specifically with grants coming from academic institutions and the National Science Foundation, but to raise, like what we have here, roughly around $1 million additional funding per year. This is only possible if we also have the support of the companies. So as you can see from the academic grants, we get something around half. The other half is coming from companies. Okay, so that's basically the structure that we have right now. You can see here quite variety of companies going from high performance computing like IBM or Sun to completely other side of the spectrum. You could say Nestlé Research. I wanted to explain you why we are working on these areas, because some of the technologies that we develop are actually applicable to both domains. And I will try to explain that very briefly without entering into the technical details why we are doing this. Okay, bottom line here from the message, I would like to say that it's feasible, but that intrinsically requires to have or being willing to support a relatively mixture between senior and junior people, and in the end, whatever you want or not, the lab becomes a little bit big. There's no way to have a good transfer of science plus technology transfer with senior people with having 5 members in the team. It doesn't work like that. Okay, so like I said, the areas of research is basically computer engineering. So what we have, our basic background and my own background since my PhD in the 90s, I would say, is basically on design methodologies. So what we build always are methodologies or flows that will help companies or tackle new type of scientific problems of mapping applications onto the hardware or building hardware specifically for a certain problem which is new that is not been solved yet. Okay? So we are building both hardware and software solutions. And these are the different aspects we are going to try to tackle. So I'm going to focus specifically on two areas, thermal and energy aware design. So basically you take computers today, your laptop or whatever, you have a multi-core system. We have all heard about this idea of multi-core processors. So you have multiple processors there, but these processors have been built after a lot of exercises of trying and finding errors on power consumption. We still have a lot of troubles on the phones. You see that your phone does not last for 3 weeks, which you would like to, it lasts a few days. We are still trying to solve that, but for laptops and other technologies have been quite stable by now. So this is one of the areas that we work on, trying to fix this problem. The second one is on completely other scope, which is trying to build really long-term monitoring systems for medical applications. And in that sense, we are specifically targeting, and I will show you some of the examples with a specific signal, which is the heart. I'm going to show you examples with electrocardiogram. How can you do electrocardiogram analysis in an advanced way without having to monitor it with the support of the doctor next to it? And in fact, the startup that we will present later, that Paulo will give you an illustration of that. He was one of my previous PhD students and has created a startup on that. He will explain you how we have developed the startup coming from these ideas on the scientific side. So let me start with the part of the multiprocessor design. So what you could see, and just to illustrate very briefly, you have architecture like this with multiple processors, what you have in your laptops today and so on. And many of them, they were trying to be composed by having the same things that you had before in the previous computers, trying to put many of them together. Okay? The main issue of that is that suddenly you see that the temperature of your laptop was going up, and you put many of these things together, basically you start having a lot of hotspots and points that actually stop working. What they were doing, and actually you find sometimes still in many of the laptops today, is that suddenly you are working and the fan starts, and then your thing crashes or stops for a while, trying to cool it down. So the main idea is that this can be solved by anticipating these problems. So what we have been working is on methodologies to anticipate these problems and try to fix the problem before it happens. So anticipate what is going to happen. So this was a project that started even before I joined EPFL in 2007 when I was visiting Stanford, and there we found out that there has to be something to be done instead of having these large fan systems on the servers and so on. So for doing that, we built the first project, and that was already a cooperation with a company. Just to illustrate the problem that happened here. Everybody was saying these issues when I was in Stanford, but you will never have access to this thing if you don't have access to the latest computer that is being built at that moment, that experiences these problems. What is the issue here? You don't involve the company will never share the information with you. Why? Because you're going to start giving a lot of bad publicity about them. So you first have to sign a lot of confidentiality agreements to get the access to the information, and second, you have to be ready to not publish anything. Okay, once you start doing that, this is an exercise that you will say very painful, and very often we don't want to do it, but in this case, the main or long-term goal that I had was if I start having like this and I convince them that there are things that are fundamental problems in science, I can also try to publish the results without compromising the results, the name of Sun or Oracle at that moment, but just to show that they are at the forefront and providing solutions that are not yet fixed by other companies. So that's how we built it. So we started having an understanding of the problem, we understood the issues, and we came up with something that was much better. So you see here there are no red points, so there's no need to activate the fan. That's the idea. So based on that, the outcome of this exercise, while we spent 2.5 years without publishing anything, was after that when I joined EPFL, Oracle was willing to let me continue the work by having industrial grants directly given to the lab to work on their designs, and at the end, we were able to publish some of the outcomes of the fundamental methodologies, not applied to some, but applied to many other things, and many of the companies even follow. So as a result of that, we got in touch with many other companies, and we got actually even an award from Oracle as a basic researcher enabling many of their products. So that was a way to give something up front, compromise not to publish for a while, but then in the end turns out to be something we're still working with them. Okay? The second exercise was actually started when I joined EPFL, thanks to a research project coming from the National Science Foundation. So they had a project, they have a program which is called Nanotera, where they actively try to engage companies to present problems that we try to solve in the academic institution. So in this way, it gave me a chance to interface with IBM Zurich, where they were having problems trying to build servers that will consume less energy. Today, data centers consume roughly between 30 to 40%. They generate 30 to 40% of the carbon footprint, and they consume almost 10% of the energy that they have in civilized worlds. So what they actually, well, can we reduce that? That will give us a huge benefit in front of the competitors. So we built the idea of creating what we call intelligent data centers. And this idea was translated to the idea zero emission data center, which is called, the project was called CMOSAIC. And the idea is that we have a server where instead of using air to cool down the server, we will use water. And the water will jump into the server. Okay, so the water will really fed onto the chip itself. Okay, normal water, not nitrogen or anything like that like it was done in the past. So non-expensive water will actually jump onto the server, and that's what we have here. So we will build chips with microchannels where the water flows onto the chip, and in the end we will have a system that will be able to take out the water with the heat that was generated from the server, so costing pretty much nothing, so no air consumed at that moment, and this heated water could be actually reused to heat up the buildings around the data center. So in fact we had a demonstrator which is the Aquasal server, where we show that in this technology you can recover up to 80% of the energy that you were using theoretically initially for the cooling of the servers. So when we did that, basically the conclusion was, first of all, IBM was very interested. They wanted to, we already created the idea, why don't we have a startup on this new technology and try to do it? Well, the point in this case was that at this particular case, IBM was very interested, but it was very difficult because it was not simply electrical engineering, but you have to understand all the mechanical parts, how to build the pumps and so on for the water system around it. So in the end, what we decided, this requires a lot of competences for a tiny startup or a tiny lab in this case. We kind of outsourced the whole thing to IBM, and IBM is having the whole ownership. But that was a way to create a long-term cooperation that since then we are having. So actually we have access to all the technology, and we have information from IBM that are not available to any of the labs. So an interesting aspect from that is that, well, we couldn't build that startup, but the idea of working on temperature and optimizing temperature in the systems moved from the servers to the data centers. So data centers are also having a trouble because now it's not only a problem inside the server, but the whole data center is getting hot. You have reported very often that you see Google talking about how much they save energy in cooling, these type of things that are today. Well, bottom line is that there's a huge amount of energy that goes in the maintenance of the data center, actually more than what goes into buying new equipment. So they spend more in making the servers run than whatever they buy as new equipment for the system. So in this case, what we tried to find out what was the challenges here, again, so we move with, thanks to the support of IBM, we had given all the rights in that case for them to exploit that, but they gave us access to all the data of the data centers. And thanks to that, we realized that the main problem that they have is that the fact that they have a huge segregation, and the data that they observe about how is the energy spent in the data center is very far from the actual source that consumes the energy, which are the servers, and they are not monitored properly. So what we developed was, based on our experience, tiny elements that you put into the data centers in the different servers, and they can monitor in real time what is actually the consumption of the elements on the data center. This basically automatically created the interest, which is interesting to see, not on the main vendors. IBM is interested, some other companies, Eaton is interested, but the main interested partners to want to buy that right now, which is actually a very big source of funding here in Switzerland, is banks. So the banks, they see, you go to the manager sees, well, I'm spending so much money into the maintenance of the data center, and I'm getting zero out of that, because this is cost. And I don't know to whom I should charge it in my company because the data center is shared by everybody. So can I find out that the banking for private customers is consuming so much energy, so I can charge it. Right now is the black hole, they don't know. So it's not essentially that they don't know how much energy they consume, they know, but they want to know to whom they want to charge it. Okay, so in that sense, they are very much interested in creating a startup now that we are discussing, because we built a system that was able to do all these things transparently for them. So there will be an interface that tells you, this is the unit, this is how much they consume, charge it to the unit. So the manager of the vice president of the data centers will be saying, my actual real cost is just for buying all the energy, you charge it to the units that consume the data center. Okay, so And for that sense, what we are proposing as the current solution that we have is that we have even solved a second part from the problem they have, which is whenever you want to instrument a data center, any solution today, you have to put wires. You have to wire the whole data center with sensors. So thanks to what we know, we were able to build a wireless solution. So technologies are there, are not essentially new. You need to find what is the hotspot for the companies. And to be able to do that, you need to know the companies. So our experience is that if you give a little bit upfront, in the end, you actually can leverage quite a bit of things with the companies if you know a bit of the area they are working on. So this is a new startup that we have. The product that we are proposing is called PMSM, and actually Andre is pretty much aware of this development that we are doing, and I cannot tell you more because still we have to discuss with Credit Suisse how it's doing, but they want to have their investment funding directly providing funding for the startup. Then I'm going to actually conclude something where I can give you a bit more details, which is the other area that we have, which is the design of new monitoring systems for humans. So in that sense, what we try to build is something that addresses the current problem that has been quite clear for the World Health Organization since 2005. So basically, they noticed in the first study that they did already and published in 2006 that most of the infectious diseases that you have today that cause trouble and deaths are a very insignificant amount with respect to the overall deaths that we have in the world. Okay? Especially in civilized countries, you see that the amount of things that are related to health or personal lifestyle, how much we move, how much we eat with respect to that, represent almost 50% of the deaths, or are close to 50% of the deaths. So we wanted to do something that will help this type of way, to help this problem, but to do that you don't have to really create a mechanism to go and do a simple monitoring, but you need to be monitored all the time. So for example, if you have diabetes, the diabetes does not get developed in a matter of minutes or weeks or even months. You need to have something that is continuously monitoring you, and ideally you will not use it if it's not really transparent, so it doesn't bother you. So we wanted to have something that was, instead of symptom-based, that you have to go to the hospital, something preventive. And the second area, after talking to quite a few of the doctors here, to have something that was not hospital-centered, but more person-centered. So in that sense, we came up with the idea of building a number of sensor nodes, number of little sensors. I'm going to show you a few examples in a second, that can monitor different biosignals and can diagnose directly what happens. And this can then inform directly the doctors and take a decision. And that was the first prototype that we built with a startup that Pablo is going to show you, which you have the device and it's able to connect to a phone and shows in real time what is the diagnosis of the device. So what we had to do here, and actually you needed to have quite a lot of support here because it was not our main expertise, is on the signal processing part. So to be able to do this tech transfer process, you needed to have doctors behind. So since the beginning, I would say one of the main challenges that we have in that area was to find out the right set of experts that will help us, because it's not just building electronics, but it's building electronics with a medical value. So in that sense, before you embark in any of these things, and that's what we learned after doing a couple of attempts that were not successful, is that you really need to start from saying who are the users that are going to find what we are going to develop. So in that sense, we realized that the ones that are going to make a decision saying, yes, this device is useful for me, are the doctors. So we went to the doctors, especially with the SHUB here, the University Hospital in Lausanne, that we created the link thanks to the tech transfer office. And with that, we went to there, we proposed them the idea, and thanks to that, we refined what was the concept. Okay, and it came up in the end that they wanted to have something that will filter all the noise. So instead of getting hundreds of minutes of things that they need to diagnose, they will, which are with noise and so on, they will have only signal that is clean, and at the same time, not even hours. I want to just diagnose the moment when actually something goes wrong. So we built all this, we built a device that was able to filter all this, and in the end, it came to something that the doctor will receive just when the moment happens. And the doctor will say, yes, it's something that I need to care about, or forget it. Why? The simple reason is if you take the decision yourself, you are liable, and that's actually what we have learned with the company later on. We cannot take a decision. We can only help the doctor take a decision. But that's already a huge value for them. Okay, so our initial attempt was, we want to replace the doctor, we do everything on our side. That was wrong, completely wrong, because it would not go anywhere, we would not have any kind of success anywhere. In the end, we came up to something that was much easier. We need to do what we know well. We filter the signal, we produce you a device that is tiny, that the patient can use, and you take the decision. But we only bother you every now and then that we have quite likely a symptom that you need to diagnose. The doctors were very happy with that. We had, of course, partners for that. So we have several grants that came from the Nestlé Research Center and Health Science in the region that were very interested about this new concept of making smart ECG sensors. We also had support from the hardware side to build a new family of processors, and from there came actually the real value of the company, because we had a number of patents that we could actually show to the potential business investors, that actually we have not only the expertise, but we have several unique things that you cannot replicate outside, that we will actually go and leave to the company to exploit commercially. And that's what we actually did. The overall solution is what I'm going to show you in a second. It's a system that can last more than 20 days, 25 days with a single battery recharge. So you give it to a person and the person goes home, and the doctor, if something happens, will receive the information automatically. And that's basically the main point where it actually came up. As a side part, I would like to also outline that we had the patents, but there was also a lot of research. So we had a lot of fundamental conclusions about what type of analysis and filters you can do in the signal without losing the actual ECG signal. And that was part of 2 PhDs that have actually just graduated. Actually, if I take Pablo, 3, and then Pablo has joined the company itself. So apart from the interesting aspect from the scientific viewpoint on the analysis, development of new sensors, it can also have a lot of impact on the medical community, like I mentioned. The main effort that we did on that was, well, we contacted several doctors. The several doctors that have much more influence to get to the media, they contacted different TV channels and different magazines and so on. And we actually had a study promoted by CNN, where we put the same device to 100 patients, monitored by the doctors, of course. And based on that, these were people that have potential pathologies, but that were not clearly diagnosed. They were not able to diagnose with traditional systems, which is what they call Holter, which is a device they put, they record the signal, and after a while they bring it back to the hospital and checks. The arrhythmias were so random that they were not able to really diagnose something consistent. And they were not really able to find, which was most important for the doctor, the source of the arrhythmias. So what came out as a conclusion was interesting, was that many of the problems that these patients that think they have something is actually in the brain, it's not in the heart. And what they did, in fact, was they were using the devices. At the beginning, what was a surprise for us was the device was supposed to work for 4 weeks, 25 days. Actually, the device was getting discharged very fast. We could see that because we were able to monitor the battery and connect to the device. And we were surprised why. And the point was that at the beginning, when you put it in a patient, the patient will be so worried that the device is working that will be every 5 minutes checking the device. So taking the phone out and checking if the thing is working or not. After a while, the patient will see that yes, the device is working, and will stop checking the device, and will get much calmer. And indeed, the conclusion was that patients that were having these pathologies, in the end, that were very often with the Holter device going to the hospital before the Holter process was finished, here they were not coming anymore. Okay, so in the end, the conclusion was that you could reduce 50 to 60% the visits that the doctor will need to handle if you put these devices, smart devices, on the people. That created a lot of interest on the doctors because they reduced the load that what they had to handle. So that's the main thing. So based on that, we decided to really move forward with a startup. So we created a startup that it was strongly supported by EPFL. So here I have to really outline the strong support that we had from different sources of the Tech Transfer Office. First of all, with the support of filing the patents and how to actually do that we did at the lab side, but in the end, they help us to find the right lawyer and so on. You don't have that in other universities that have been, forget it. You will never be able to do it. So you need to have a specialized unit that really helps you on the things that are not really research oriented, because neither me nor my students were really lawyers to create patents. You need to have somebody that tells you this, that yes, this is meaningful, this is not meaningful. At the same time, you need to find the right customers in that sense. We knew the doctors, but we didn't know who will be the companies that will be, or the venture capitalists that will invest on the companies. So these things, a unit has to help you. And in this case was very successful, the collaboration with the tech transfer office. At the same time, you need to have, if possible, at the regional level support. In this case, we have two types of supports. First of all, CTI, which is the global unit actually that exists to actually support companies' startup creation. So we enter into the CTI coaching program. So we have a coach, a business development coach that helps us on how to build the company. And at the same time, EPFL has a program which is called InnoGrant. I'm not sure you have, if they have already mentioned to you, but that was also very helpful for us. We got an InnoGrant that will support basically the salary of one of the students until we manage to come up with something that we can sell to the business that is really mature enough, because from the prototype on the lab to the actual device, there's a longer step. So here, this will help, covering one student. And in the end, we actually managed to have even support from a competition. We won a second InnoGrant. So actually, we got kind of 1.5 InnoGrants almost guaranteed for that. And this will help us quite a bit on developing a mature product to present to possible investors. And actually, that's what you're going to see next. So with this, I think I conclude. I hope I have illustrated a little bit how you can combine science with tech transfer, a little bit, and I'm open for any questions you have. Otherwise, what we can do is we can have the presentation from Pablo on the startup, if you want. Oh, yes?
I have a more technical question. When you use the signal, you said you do, as I understand it, an anomaly detection or outlier detection of the signal.
Yes.
Do you use the classification or clustering techniques?
Okay, so it's a very interesting one. So there are many different things that we can do. The first thing that we actually have is that you have to do several steps. So you first have to filter the signal. Otherwise, the classification or whatever you want to do there, you will not be able to find any pattern that will match your thing. Second thing, to find a pattern, what you need to have, and that's what we have, is a long interaction with the doctors about what they really look at when they look at the signals. So you don't really do, we didn't do classification in the first phase. We just simply looking at the full signal delineated that you will do in equipment from the hospital, but in an embedded device, and look at what the doctor will look at as possible anomalies. And based on that, we report to the doctor, and we came up with a database of around 30 pathologies, which is the 30 effects that what the doctor will look at as main sources. And then between them and other minor pathologies, it's very difficult to diagnose for us. And in any case, it's not really meaningful because the doctor will need to check it himself. So the current devices that you have there are able to distinguish between 30 to 40 pathologies, depending on the variation that we use of the device that we commercialize. And then it's the doctor that decides. After that, as a research side, what we have done is, can you really fully automate, and I'm not saying we are going to do that, the company will not survive with that, but can you really remove the doctor from there? And really extreme cases do it. And we have shown in very recent papers that for most of these pathologies, yes, we can actually do that. So we can even save sending the data to the doctor. Imagine that you are in a desertic place and you don't have wireless communication. You cannot send it to the doctor to get a diagnosis, but the patient needs to know. So in that case, we are able to even make a final diagnosis on the device. But that is something that, to be honest with you, I don't have so much confidence that we'll be able to commercialize. Because the one that has to take the decision to use these devices is the doctor, and the doctor will not want to be liable saying, this device replaces me. So that's why we move to the other side. Yes, for the company.
Yeah, because you need to be approved to practice medicine, and a company cannot practice medicine. A human being needs to pass exams in order to have the right to practice medicine. So I don't know if a device can be attested.
Well, you have different type of certifications that you have. So we are doing right now, and actually Paulo will mention that, of course, to be able to commercialize the devices, you need to have, in Europe, the CE certification, in the US, a different type of certification. You can have certifications as a company, not as a lab. So that we have the company, we can pass certifications. What you have to distinguish is which type of certification you give to your device. You can give the certification to your device as a monitoring device, okay? That you guarantee that you are doing a good monitoring and you are not skipping events that are meaningful for the doctor. That's one certification. And you can have a different type of certification saying, I'm not only a monitoring device, but I'm also a diagnosis device. completely different story, completely different budget, and completely different cost. So in this case, the one that we see that there is a value, and the doctors, like I said, in this study that we did with CNN, we say yes, is the monitoring one, not the diagnosis one. Of course, there's much more money in the other one, but that requires to recruit all the doctors and that they have to agree on something. Any other questions? So then I let you, as a second thought, this is the professor view, I let you the student view. He has been the one working on the startup.